Welcome to this A-level physics lesson on electric field strength. Now let's start by looking at something we already know about, which is gravitational field strength. Now we know that gravitational field strength, little g, is given as the force per unit mass on an object found in a gravitational field. This is why its units are newtons per kilogram. Now we have a similar concept in electric fields. Electric fields, given by E, so we have electric field strength, is the force per unit charge. So we have this time the units of newtons per coulomb. So that is to say, it is the force on a charged object per unit charge in an electric field. So that is the electric field strength. Now we need to know in particular about a special case. This special case is when we have two charged plates. So if we have two charged metal plates, the charge will spread itself out evenly on each plate because the plate is a conductor and it contains delocalized electrons. Now that means that the electrostatic field lines between these two plates will be uniform. That is to say that all of these lines will be perfectly parallel. Now as a result, not only will they be parallel, they'll also be the same distance apart, even though my drawing isn't very good. And because they're the same distance apart, that tells us that the electrostatic field strength, or the electric field strength, is the same everywhere between these two plates. So that means the force per unit charge between these plates is the same everywhere. Now this tells us that if we have the force per unit charge, so the force on a small charge between these electrostatic plates is F equals QE. Now, we're going to look at how this varies with the distance between these two plates, because this is an important factor, as well as the potential difference between these two plates. The reason we're looking at this is because a little later on we will be looking at capacitors, and capacitors are charged plates which are able to store energy. So, if we have the force on a small charge between these two plates is Q times E, the charge times by the electrostatic field strength, we can also recognise that there will be work done in moving that charge. So assume a small positive test charge, there will be work done in moving that charge towards the positive end. So we can say that work done equals force times distance moved along the line of action of that force. So we have D. This means we can put these two equations together, because as we can see, force here is also QE. So we can say that the work done is QED. Now once we do that, we can think to ourselves for a moment, we know another equation that relates work done and charge. That equation is the equation linking potential difference. Potential difference is the work done per unit charge. So if we look at these two equations, we can put these together also. We can see that if we rearrange to make W over Q the subject, we can make W over Q is equal to ED, which means the potential difference between two plates is the electrostatic field strength times by the distance. And conversely, we can say that the electrostatic field strength is equal to the potential difference divided by the distance between those two plates.